In Chapter 2, Section 6, we are talking about the combination and composition of functions. Now, this may feel unfamiliar to you at first, but if you think about it, we combine functions all the time. Whenever you go shopping, you pay not just what you have purchased, but you also pay tax on top of that. So first you have to calculate how much your purchases add up to. Then you have to plug that value in to calculate tax and add that on to the purchase price. When you go to work, there is a calculation for the amount of withholding. They take your gross pay and then figure out what percentage needs to be withheld to get your take-home pay. So those are examples of combined or composite functions where you take the output of one function and use it as the input of another. Whenever you're combining two or more functions in some way, remember to pay attention to any limits on the domains of the original function. If it won't work in the first function, if it's outside the domain of the first function, then it is also outside the domain of the combined function. For that reason, you have to remember to always think about the domain before you simplify your functions. So we're going to start there. We are going to work on finding restricted domains. We are going to look for values that would cause the function to be undefined or imaginary, because imaginary outputs are not good for us. The imaginary outputs do not show up on our graph. Okay, the first function that we have, f of x, is a linear function. Instead of doing a lot of arithmetic to try to figure out our domain, we're gonna stop and think about what we know. Conceptually, our parent functions, what do we have? Well, we have a linear function. What do we know about the domain of a linear function? Well, there are no restrictions on the domain of a linear function as long as it's not a constant function. And a constant function would be just a constant. It would not have that x variable. Because it's a linear function, there's no restrictions on the domain, so my domain is all real numbers. What about b? What type of function do we have for b? Well, it's a squared function, degree 2, so it's quadratic. We know what the graph of a quadratic function looks like. It's a parabola. The domain of our quadratic function is also always all real numbers. That doesn't change no matter what transformations we have done, so we know we don't have any restrictions on our domain. C, however, we need to be a little more careful with. What type of function is C? Well, this is in my square root family of functions. And if you think about what the graph of the parent square root looks like, let's just go over here and let's see if we had y equals square root x, that has limits. It's that little half parabola right there. It has a limit on the domain as well as the range. The limit on the domain depends upon the transformations of the function. So when we have a square root function, we know we are going to have limits on our domain. The limit is going to depend upon what we have in that square root family of functions. Here's how we can figure out what the limits are on our domain. Look at the radicand, the expression underneath the radical. I'm going to take that radicand and I'm going to say, you know what? This needs to be not negative. Because if this result, if I simplify this, plug something in for x and simplify, and it comes out to be negative, I have the square root of a negative number, and the square root of a negative number is imaginary. I want to restrict x so that I do not end up with imaginary values. Since I don't want this expression to be negative, that means it's okay if it's positive or if it's 0. I want this expression, when simplified, to be sure to be greater than or equal to 0. Square root of 0 is 0. That's fine. Square root of any positive value is a real number. That's fine. What I don't want is for that expression to simplify and be less than 0. So this is the inequality I need to focus on. Now I solve an inequality just like I would solve an equation. with one exception. If it's negative, if I have to multiply or divide by a negative across that inequality symbol, it would reverse the inequality. But right here, I'm just adding. So I'm going to add 2 to both sides, and I get that x needs to be greater than or equal to 2. This is what my domain needs to be. Well, what does that mean as far as an interval? If I throw this on a number line and I've got 2 here, I'm interested in values that are greater than or equal to 2. So greater than or equal to 2 is from 2 inclusive all the way this way. And if I take that second to sketch a number line, that shows me exactly what my interval should look like. My domain is from 2 to positive infinity. Now it gets really tempting to try to get in too big a hurry here and not take the minute or two that it would take you to do this work. And if you get in a hurry, you are likely sometimes to guess wrong. Don't guess and lose points and get something wrong. Take a second to work out your inequality. Now for C, we had the square root of x minus 2. We said, you know what, as long as that's not negative, we're good. So we're going to do greater than or equal to 0. On D, we still have that square root symbol, but the square root is in my denominator. Anytime I have a variable anywhere in my denominator, I have what we call a rational function. And rational functions I have to be careful with. A rational function is when I have an x in my denominator. My variable shows up in my denominator. Now, it's still a square root, so we for sure don't want it to be negative, right? Because the square root of a negative is imaginary. Is 0 okay here? Well, 0 is fine here. Square root of 0 is 0. But is 0 fine here? Not this time. Because the square root of 0 is 0, and 5 divided by 0 is undefined. Division by 0 is undefined. It doesn't work for us. So when I look at this inequality here, instead of x minus 2 being greater than or equal to 0, x minus 2, I have to keep that positive. 0 is not okay in the denominator. Because this is a rational function, I have an additional restriction. So I solve this the same way, but now I have x greater than 2, not x greater than or equal to 2. When I sketch that on my number line, same boundary, but now when I visualize it, I don't have a square bracket, I have a curved parenthesis because 2 is not included. I can include 2.0000001, but I can't include 2. So my domain looks a little different. That difference, though, is important. All right, let's look at E. Let's go to the next page and look at E. G of x. Okay, I got lots of stuff going on here. I have a rational function. I recognize that because I do have a variable in my denominator. I also have a variable in my numerator, and I need to stop and think, does my numerator cause me any difficulty? If I plug in any possible real number for x, is it okay? Well, sure, yeah. 5 times x, x in my numerator is fine. A negative up here is fine because there's no square root. So x can be anything as far as my numerator is concerned. I don't need to worry about that. I do need to be concerned about this denominator, however. I have this radicand. Radicand is just radicand. That's just my word for the expression underneath the radical. I have this radicand in my denominator, and I need to make sure that it's not going to give me something that causes problems. Because it's in the denominator, if I simplify that expression, it has to be positive. Can't be 0 because division by 0 is undefined. So I need to solve for x here. My first step is going to be to move that 24 over, so I subtract it, and I have negative 3x is greater than negative 24. To finish solving for x, I'm going to have to divide by that coefficient, negative 3. Now, remember me mentioning this a while ago? When you divide across an inequality by a negative, it reverses that inequality. So instead of x greater than, now I have x less than. Negative 24 divided by negative 3 is a positive 8. So let me say that again. when I divide or multiply by a negative across the inequality symbol, it reverses that inequality. So my domain is limited to all x values less than 8. And what does that look like? Well, I'm not including 8. I'm doing everything to this direction. So my domain is from negative infinity up to not including 8. That's the restriction on my domain. If you hadn't taken the time to write this out, you probably wouldn't have reversed that inequality and you would have ended up with the wrong end. So be careful about that. Okay, let's look at this next one. I'm going to kind of, because I like to have clearly defined spaces that I'm working in. I know that I've got the problem that I'm focusing on. Sorry, guys. That's just me. Okay, for f, I have h of x. I have a radical in my numerator, and I have a variable in my denominator. So I have a rational equation here, a rational function, but I have restrictions coming from two directions. From my numerator, I've got this radicand x minus 2. Is 0 okay in my numerator? Yeah, 0 over something is fine. So I set that inequality as greater than or equal to 0. So this gives me x greater than or equal to 2. That's where I start thinking about my domain. I'm limiting it to x values that are greater than or equal to 2. So I've got this limitation from my numerator. I also, however, have a limitation in my denominator. Division by 0 is undefined. So anything that causes me to have a 0 in my denominator is going to have to be kicked out of my domain. Well, what would make that denominator equal to 0? What would cause me to have a problem? If I solve that to see what would make it equal to 0, I get that x minus 5 or x equals 5. If x is 5, I have a 0 in my denominator, and that's not okay. That causes my function to be undefined. So from my numerator, I've restricted to everything bigger than 2. 2 and everything bigger, but I have to kick out 5. So I'm going to say, you know what? 5 over here has to be excluded. So I can have from 2 up to 5, skip 5, everything else. So let's see what that looks like. I need to use 2 intervals. 2 inclusive up to 5, not including 5, or 5 to positive infinity. That's how I write that restricted domain to reflect what I can use as x values. I have to pick values that fit in one of these 2 intervals when I plug them into my function, or I'm going to get out something that does not work. It's either going to be imaginary or undefined. Okay, let's look at g. Once again, I have variables in my numerator and denominator. I want to evaluate, okay, what do I need to worry about here? Well, my numerator, it's okay if it's negative, it's okay if it's positive, it's okay if it's 0. I don't have any problems for my numerator. I'm only interested in looking for restrictions in my denominator. I have a square root, so I pull out that radicand. Because it's in the denominator, it has to be positive, greater than 0. And then I solve. I move that 7 over, 2x greater than negative 7. I'm dividing here, but I'm dividing by a positive, so it does not reverse my inequality symbol. What I end up with is x greater than negative 7/2 as my domain. So when I put that down on a number line, I'm interested in the values greater than but not including that. So my domain is from negative 7/2 not inclusive to positive infinity. H. Here I have g of x. I need to worry about excluding a value from my denominator, and I need to worry about limiting values from my numerator because I have this square root. Square root is in my numerator, 0 is fine in the numerator. So I start with the inequality greater than or equal to 0. I move that 6 over by adding it, and then I divide by 3. Nothing reverses because I divided by a positive value. So my starting point for this domain here is going to be x values greater than or equal to 2. Now I need to look at my denominator. Remember, my denominator cannot be 0. If it's 0, my function is undefined. So I see, okay, what would make my denominator equal 0? What could cause that to happen? I move that 8 over. I have 2x equals 8, or x equals 4. That can't be. If x is 4, my denominator is 0. So I have to kick that value out. So I say, you know what? Everything here except 4. So again, 2 intervals for my domain, leaving out that value of 4. Okay, one final example here before we move on to something else. On I have h of x. I have x plus 7 in my numerator. Nothing wrong there. It can be whatever it wants to be. Any value for x is fine. I don't have a radical in my denominator, but I do have a quadratic expression. Remember that my denominator can't be 0, so I need to bring this over and say, okay, what would make that equal 0? Because I have to leave those values out. Anything that makes that happen is not okay, because 0 in the denominator is not okay. Let's factor this. Anytime we have quadratic, we want to try to factor. My signs are the same, and they're both positive. I see that from the middle term. Factors of 8 that add to give me 6. Well, 8 could be 8 times 1, or 4 times 2. 4 plus 2 is 6, so I'm going to use that. So I get 2 factors that I need to set equal to 0. I figure out that if I have either -2 or -4, I would have a 0 in my denominator. Since those two values would cause me to have a 0 in the denominator, I have to exclude both of those values from my domain. Now, from least to greatest, -4 is less than -2, so that's what my number line looks like. Those are the two values I have to kick out. I can use anything else, any other real number. You see that you have 1, 2, 3 intervals if you want to write this in interval notation. I'm going to show you interval notation, and then I'm going to show you another way to write this that's a little easier. I'm not sure, I can never remember exactly when MyMathLab picks up and stops using interval notation and starts using set builder notation, but set builder notation is a lot easier here. Set builder notation is just another way to show what you exclude from your domain. Set builder notation, I say my domain exists as, and I open fancy braces, all values x such that, and that's what that line means. You read that line as such that, and then I say x is not equal to -4, -2, and I close my fancy braces. So this, you can see that's a lot more succinct than all my intervals. This is what we call set builder rather than interval notation. It's just another way to represent your answer. You're going to start seeing that more as we move throughout the semester. Okay, combining functions with 4 basic operations. We've looked at how we restrict the domain. Now we're going to start looking at how we combine functions. When you talk about combining functions, there are 2 different ways to do so. You can either combine functions using basic arithmetic operations, algebraic operations, adding, subtracting, multiplying, and dividing, or you can do so using composition of functions. Let's focus first on adding, subtracting, multiplying, and dividing. If I find the sum of 2 functions, I am adding f of x plus g of x. So f plus g of x is the same thing as f of x plus g of x. And I'm literally just adding the 2 functions together. Now let me give us a couple of functions to work with so we can get an example in our notes of what this looks like. We're going to use f of x as x plus 3, a nice simple linear function, and g of x is going to be 2x minus 5, again a nice simple linear function. Because these are both linear functions, they have a domain that is all real numbers. There are no restrictions on the domain of either one of these functions. If I am told to add the two functions together to find the sum, f plus g of x, I am literally taking the first function, in this case x plus 3, and I am adding it to the second function, 2x minus 5. When I do so, I get 3x minus 2, because 3 minus 5 is negative 2. That is f plus g of x. It's still a linear function. It still has a domain of all real numbers. Okay, let's look at finding the difference. The difference is the answer to a subtraction problem. So I'm working with f minus g of x, which is the same thing as taking f of x and subtracting g of x from it. When I do this arithmetic, I have my first function, x plus 3. I'm subtracting the next function, so I need to put that in parentheses to emphasize that I'm changing the sign on every term inside that function when I subtract it. So x minus 2x is a negative x, and this negative minus 5 becomes a plus 5, so I have a positive 3 and a positive 5. For negative x plus 8. Again, a linear function still has all real numbers as its domain. The product is the answer to a multiplication problem. F times g of x is the same thing as the function f of x multiplied by the function g of x. A quick caution here, when you're showing multiplication, make sure you do a dot, not an open circle. An open circle is my symbol for composition of functions that we're going to get to next. So if I'm multiplying these two functions together, in this case, I would have x plus 3 as f of x times 2x minus 5 as g of x. And I'm going to FOIL those together because they are binomial functions. X times 2x gives me 2x squared. My outside product would be negative 5x. My inside product would be positive 6x. When I combine those two products together, I get plus x. 3 times negative 5 is negative 15. All right, there is f times g of x. If you can't do this without writing down the four products, take the time to write those down. Write it all down, combine your like terms, and then get your final result. This is quadratic. My domain for a quadratic function is the same as the domain for my original functions, still all real numbers. What about finding the quotient? Well, quotient is the answer to a division problem. So I have f of x divided by g of x, and here we have something that's presented a little bit differently. Suddenly, I have a denominator. I'm taking an entire function, in this case g of x, and I'm putting it into my denominator, which means now I have an x in my denominator. I don't have something with all real numbers as the domain. I have a rational function. So I need to be careful. This is lowest terms. I want to check to see if I can reduce anything, but this particular quotient is lowest terms, so I don't need to simplify, but I do need to check my domain. When I add, subtract, and multiply, the domain of the combined function is going to be the same as the domain of the original functions. There will be no new restrictions. But let's mark that down over here. Same domain as the original functions. However, when I find a quotient, I may, not always, but I may have new restrictions on the domain. So anytime I find a quotient, when I combine two functions using division, I need to check my domain for that quotient. Well, I have a denominator here with an x, so I need to see what would cause that to be 0. That value has to be excluded from the domain. If I solve, I get x equals a positive 5/2. That is the value that has to be excluded from the domain because it would cause a 0 in my denominator, and division by 0 is undefined. So if I'm using interval notation, I have two intervals from negative infinity to 5/2 or 5/2 to positive infinity. That leaves out that value that would cause our function to be undefined. Okay, We have some examples here for combining functions using algebra, using our 4 basic operations. We're going to work through these kind of quickly, and then we're going to talk about composition of functions. So this video is going to be a little bit longer. Now, when I use the 2 given functions, I'm changing. I have 2 new functions for f of x and g of x. Instead of linear functions, I have a square root function and I have a quadratic function. Now, my square root function has limits on the domain. When I look at square root of x, I need to make sure that that is 0 or positive. So I can't use a negative value for x. So my domain for this function is 0 to positive infinity. Quadratic function, it has a domain of all real numbers. Oops, negative infinity to positive infinity. There we go, all real numbers. When I am considering the domain, if I'm adding, subtracting, or multiplying, I will use my more restricted domain here. So the domain of functions, combined functions using addition, subtraction, or multiplication will have a domain of 0 to positive infinity so that we don't have to worry about plugging in something to the combined function that will cause a problem. So we looked at the domain of each individual function. That's what we did here, domain of f of x, domain of g of x. So if I'm going to add, subtract, or multiply, I'm going to use the domain as 0 to positive infinity. If I'm going to divide, I have to check for new restrictions. So you can see for numbers 2, 3, and 4, the domain for the combined function is going to be 0 inclusive to positive infinity. But on number 5, I'm going to have to be a little bit more careful. Number 2 says to do f minus g of x. So I'm taking the function f of x, 3 square root x minus 2, and I'm subtracting. So I'm going to put in parentheses g of x squared plus 5. I need to distribute that negative. 3 square root of x minus 2 minus x squared minus 5. And I look at that, and do I have any like terms? Well, yeah, I have negative 2 and I have negative 5. So I get, let's do correct order. So we do our x squared term first. Negative x squared plus 3 square roots of x minus 7. Okay, our second problem says to find f plus g of 4. So I'm going to add the 2 functions together, and I'm going to replace x with 4. Another way to look at that would be to do f of 4 plus g of 4. If I'm only doing a single example, if I'm not plugging in multiple values, it's easier just to plug in that value first. So let's do that. Let's do f of 4. Well, f of 4 would be 3 square root 4 minus 2. And then I'm going to add to that, that's my f of 4. I'm going to add to that g of 4. Well, g of 4 would be 4 squared plus 5. Let's see what we can simplify. Square root 4 is 2, and 3 times 2 is 6. Then I have minus 2 plus 4 squared is 16 plus 5. When I do my arithmetic here, 6 minus 2 is 4, plus 16 is 20, plus 5 is 25. Excellent. All right, let's do f times g of 0. Again, if I'm just doing a single value, it's just as easy to plug it in to start with. So I'm going to do f of 0 times g of 0. Well, f of 0, 3 square root 0 minus 2, 3 square root 0 minus 2, times g of 0, 0 squared plus 5. Okay, order of operations, simplify inside your groupings. So in that first set of parentheses, square root 0 is 0, times 3, anything times 0 is 0, minus 2. My second set of parentheses, 0 squared is 0, plus 5. So I have negative 2, times 5 is a negative 10. Okay, now we have a division problem. All right, I'm going to change colors here. And we are finding f divided by g of 9. Is 9 in my domain? Well, we know that we have to use the domain from 0 to positive infinity for these three problems, but now I've suddenly put g, the function g of x, in my denominator. So let's look at g of x. Can I use 9 fits here, so that's fine. Is 9 going to cause me a problem if this is my denominator? No, we're fine. Okay, so f of 9 over g of 9. F of 9 would be 3 square root 9 minus 2. G of 9 is 9 squared plus 5. Well, square root 9 is 3. 3 times 3 is 9. 9 squared is 81. So my numerator becomes 7 and my denominator is 86, and that is not reducible. So we are done. Just always check to make sure that when you stop, you're in lowest terms. Let's look at that last page and tackle composition of functions. With composition of functions, this is what I started talking about at the beginning of the video. When you take the output of one function and plug it in as the input of another function. Order matters with composition. If you get them out of order, you're going to get the wrong result. You can see that I have two different orders for my stated compositions. That little circle is my composition symbol. This first example says that I have f composite g of x. I would read that as f composite g of x. That means I'm taking this function g of x and I'm plugging it into the function that is mentioned first. Another way to write it is f of g of x. That's what's being plugged in. My second example, different order. G composite f of x. G composite f. That means I'm taking my function f of x and I'm plugging it into that function g of x. So I've got g of x and I'm plugging in that function f. Order matters. All right, we're going to do a few examples of these. Using the given functions, I'm giving you a new f of x, a new g of x, and a new h of x. We're going to do the composition. Make sure we do it in order. Number 1 says to find f composite g of x. So I am taking g of x and I'm plugging it into that f function. So again, that would look like taking f of x and I'm plugging in the function g of x. So my big function, the one I'm interested in then, is f of x. So I have square root of. And that x is being replaced with the g of x function. Well, g of x is 2x minus 1. 2x minus 1. And then I take a look at that, and it won't simplify. So my result is square root of 2x minus 1. Won't simplify. Let's look at number 2. Number 2 says to find f composite g of 5. So I'm taking g of 5, not x, but I'm using 5, and I'm plugging it into f. So again, to rewrite that, f of, and then I'm plugging into f, g of 5. Well, this is a lot like the last one I just did, right? F of, and then where that x was, I'm replacing, I switched colors on myself. Sorry guys, I've got this big square root that has square root of x, but instead of x, I'm using g of 5. So I'm plugging in a 5 there. So 2 times 5 minus 1. Instead of 2 times x minus 1, I'm doing g of 5. So 2 times 5 minus 1. Well, let's simplify that. We've got square root of 10 minus 1 is 9, and square root of 9 is 3. Another option would have been, you know what, I have f composite g of x. I've got that right there. I just plug in 5 for x. Now we're going to go back the other direction. Order matters. I'm taking f of x and plugging it into the g function. So my major function is g of, and I'm plugging into that f of x. So function g is what I'm starting with, 2x minus 1. So 2x minus 1, and instead of that x, I'm using that function. Square root x is my f function. So can I simplify anything? Well, no, I can drop the parentheses, but I can't simplify 2 square root x minus 1. Problem number 4 asks me to find g composite f of 5. Well, we just found g composite f of x right here. So I'm just simply going to use that and replace x with 5. So 2 square root 5 minus 1, and that doesn't simplify. Number 5, h composite g composite f of 9. Now we're going to do this a little bit differently to make it simpler for us to view. Just like we started at the end, we're going to start at the end with f of 9. So what is f of 9? Well, f of x is square root x, so f of 9 is square root 9. F of 9 is 3. I'm going to take f of 9, which is 3, and I'm going to plug it into g. So I'm going to take this 3 and I'm going to plug it into g, because that 3 is my f of 9. When I plug that into my function g of x is 2x minus 1, so I'm doing g of x is 2x minus 1, so I'm doing g of 3. So g of 3 is going to be 2 times 3 minus 1. Well, 2 times 3 is 6, minus 1 is 5. I'm supposed to take that g of f of 9, all of that, and go back again and plug it into h. So I take this output and I plug it into h. So I find h of 5. My function h is x squared. So h of 5 is 5 squared, or 25. So you can see I followed my order. I started at the end. I took the output of one function and used it as the input of the next function. That's how compositions work. My last example is finding compositions defined by sets. So I've been given 2 sets, f and g, and both sets contain 3 ordered pairs. F contains these first 3 ordered pairs, and g contains this next 3 ordered pairs. Remember our order. I'm going to find f composite g of 1. I start at the end. Well, what is g of 1? G of 1. Remember, g of 1 starts as g of x, so I'm looking for where the x value is 1. Function g, x is 1, well, g of 1 is 4. The function value for g at 1 is 4. G of 1 is 4. That's the output of this first function. I'm going to use that output and plug it into f. So I take that 4 and I say, okay, what is f of 4? Well, look at your f function. I find the x coordinate 4 and I see that the outcome is 9. So that's my final result, 9. Let's look at the next one. We start at the end, g of 2. So function g, where the x coordinate is 2, that is paired with the output 5. That output becomes the input for the next function. I plug that into f, so f of 5. I go to my f function, I find where x is 5, and that output is 10. And then my last one, f composite g of 3. I start at the end with g of 3. I go over, and where x is 3, my output is 6. The output of that function becomes the input of the next one. So I'm plugging that into the f function, and I want f of 6. Well, when I go to my f function, there isn't and x coordinate 6. 6 is not part of the domain of this function. It's outside the domain, so f of 6 does not exist. D and E does not exist. That one's not possible.